Hello everyone! In the last chapter we have seen how to use derivation trees for very efficiently producing inputs from a grammar. Today we're going to refine this idea a bit further by introducing the concept of grammar coverage. The idea of grammar coverage is very simple. The idea is to obtain a maximum of diversity in your inputs by trying not to repeat productions that you already have used and rather favor productions that you have not seen so far. So rather than producing, say, the same digit all over again, 1, 1, 1, 1, 1, 1, whatsoever, we try to obtain diversity and we say, okay, let's try to cover all digits as quickly as possible, 1, 2, 3, 5, 7, 6, and so on. And the same also goes for other features. This is important because if you have a grammar that has plenty of, say, syntactical features, commands, whatsoever, it's very obvious that each of these syntactical features corresponds to some code that actually handles it, and you want to cover this code as quickly as possible. And for this, we need to come up with a couple of refinements to our original grammar production algorithm that we have seen in the last chapter. And for this, we now introduce a new class, which is the grammar coverage fuzzer, which attempts to produce inputs that cover as much of the grammar as quickly as possible. So let me start with introducing the concept of grammar coverage. We can again go into our neat little grammar production example. Again, we're using arithmetic expressions for that purpose. And we are using this grammar for producing. So you've seen already before that we start with the start symbol and then we replace the start symbol with the right-hand side, which is the expression symbol. And the idea is now every time that we apply such an expansion, we actually mark in the grammar that we have done this already. So in this case, we already have used the expansion into expression, so we mark this that we already have used it. When we expand expression into term minus expression, we also mark term minus expression as having been used before. And now every time later, when we keep on expanding things, we will be looking for expansions that we have not used before. So let's continue this thing. Term is factor, fine, we do that. And we cross out factor in here. And we have a factor that becomes an integer dot integer. So again, we cross that out. Blap, here we go. Don't want to use this next time, or at least, well, we can use it next time, but as long as there are expansions that we haven't used, we want to prefer those which we haven't used before. Keep on doing this. Integer becomes digit, and we cross that out too. And integer here becomes another digit. This is actually not the best example. Integer should here become digit.int. I'm sorry about that. Now we have digit that becomes an 8. We cross that out. And we have another digit, and here we choose an expansion that we haven't seen before. So, and every time we keep on choosing an expansion, we pick those options that we have not seen so far. For instance, next time we expand expression, we may want to go for term plus expression because we haven't seen that so far, or for term because these things have not been used before. So this is the whole idea of coverage, of grammar coverage. This is, of course, the rather simplistic. If we only look at locally at an individual rule, then we may quickly find things that we may quickly cover individual parts that have not been used before. But the whole thing can also become more sophisticated. Namely, it could be that we may choose one of these expansions that we have used before, but later on downstream, we can reach an expansion that we have not used. This is something that we now implement in our, grammar coverage fuzzer, which does all that. It uses an internal cache to keep track of all coverage, in which we represent the expansions that we have used as individual strings, such as digit equals 0, digit equal 1, and so on. And then it goes through the individual options, keeps track of the expansions that it has used so far, and keeps on expanding and expanding while maintaining those expansions that we already have seen. This is the gist of the coverage fuzzer. It hooks into the basic algorithm of the derivation tree fuzzer that we have seen in the last chapter. And in particular, whenever we're choosing one alternative, it seeks for alternatives that still lead to uncovered parts. What happens once everything is covered? Well, then it's very simple. Then it falls back to the original algorithm, simply picking something at random. This is, of course, also something that could still be expanded. We could go, say, for covering pairs of expansion or for covering triples of expansions. There's also research on that, in particular from my group, in which you can look up. There's a paper, ASE 2019, systematically covering input structure, in which my PhD student Nicolas Havrikov has explored all this. And it turns out that not only does it help to cover individual combinations and individual elements in the grammar, but also their combinations, because these combinations then again might result in particular features of the program to be covered. So, enjoy coverage-based grammar fuzzing. As always, you can try out all the examples in the Jupyter Notebook yourself, or inspect the code at will, just to find out how things work in detail. Enjoy!